rightmost value is -2. It's negative infinity to -2. So it's either the graph is either increasing or decreasing. So again, this, you can choose this one, negative infinity to -2. It's not going to be constant in your class anywhere. Is that okay?
Yeah, that makes sense.
All right. So the
So we
the
only have
next
to worry
one,
about,
but
sorry, we only have to worry about increasing and decreasing in this class.
yes,
Okay.
yes. Like it won't be constant anywhere, which I think is a good thing. All right. So same thing here. There's just more intervals. So increasing is where it's going up and to the right. You're gonna want to identify those peaks and valleys. Okay. So like I'm gonna shade in where it's increasing. It's increasing there and increasing there. Do you agree with that? Because it's going up and to the
Yeah.
right. Okay. So it's the X values. So it's from -4 to 0. It's the X values. No, nothing to do with the Y values, just the X value. They're -4 to 0, comma. It says use a comma to separate your answers. New X value 4 to infinity.
Okay.
And then because it's either increasing or decreasing, we presume that it must be decreasing on the other intervals. So it's decreasing there and decreasing there. And you can see that. So it's decreasing from -infinity to -4, comma, 0, comma, 4.
Okay.
Any questions on that before we move on?
No, that's pretty easy so far.
Yeah, yeah, maybe looks harder than it actually is. All right, new question here, number 3. So this one is it would be so much easier if we had a graph. Okay.
Uh-huh.
Now you're going to have a calculator, which means we could graph it. If we don't have a calculator, we have to do this by hand. Um, would you like us to graph it?
Yeah, if it makes it easier.
Okay. Now I'm gonna use Desmos to graph it because it's easier, faster for us. But when you get your calculator, we can go through how to graph and find mins and maxes and stuff like that. Um, if you want, but basically I'm saying like let's do it the more efficient way today, because you don't have a calculator,
Right.
and it's easier if you can, when you got it, it'll make more sense. All right, so here's a graph of the function. Okay, so critical numbers are where the derivative is equal to 0. You're looking for what are called horizontal tangents. Basically, you're looking for either peaks or valleys, or where it's going up or where it's going down. You might say it kind of looks like one over here and over here, but it actually just keeps going forever. So this one actually has no critical numbers.
Okay.
There's none of these. These would be where your critical numbers would come from.
Okay.
You don't have any of those. Not a
Okay.
bad thing. It's just you don't have any. Now, is the graph increasing? Is it going up and to the right anywhere? Like if you trace the
Um,
curve from left to right, is this
no.
going up and to the right? Nope. And you
No.
get over here, down to the right. Nope. So it's never increasing, but it is decreasing. It's decreasing actually everywhere that it's defined. This is decreasing and this is decreasing.
Uh-huh.
So from your previous courses, you're supposed to know that where the bottom equals 0, it's what's called a vertical asymptote. So
Uh-huh.
at x equals, sorry, I graphed this wrong. Boy, I'm off today. Not that it matters. I didn't sleep well, so sleep is
So,
very
yeah,
important.
it is for the brain.
You gotta have it. So let's see if I can send this to back. All right, let's see if that's easier. Okay, so you can see here there's at x equals -1 is this vertical asymptote. and it's decreasing all the way up to that point, and then all the way down to that point. So let's fix this. So it's decreasing again the x values. So from minus infinity to -1, comma -1 to infinity. This means that it's decreasing everywhere except for -1. And you have to enter it this way. It says to but hopefully it says somewhere to like use a comma between answers. I didn't snip it all in, but I think it says comma
Okay.
somewhere.
Yeah, it's a separate.
Okay. Any questions on that?
No, so far that's good.
New question. Manufacturer sells video games with the following cost and revenue functions in dollars. The profit function is increasing on the interval. The profit function is never increasing. So profit is revenue minus cost. So you take your revenue function, which is 0.262 x squared minus 0.123 2x cubed, and you subtract 0.16 x squared minus 0.00018 x cubed, like that. That's your profit function.
Okay.
Now, I would for sure go to a calculator.
Yeah.
Okay. And the hardest part about graphing this on the TI 384 is the getting the window right. So that's why I'd like to show it. You have some strategies for making that faster when you get to the test. For now, I will graph it on Desmos, and just a moment here to get that in. Revenue minus cost. Huh. Sorry, I'm just looking to see if I've actually entered this correctly. I think I left out a 0.
Okay.
There it is. Okay, there we go. Like, why doesn't this graph didn't look like? So the biggest challenge with graphing is just entering it incorrectly, which I failed to do. But let me get a snip of this here in a moment. All right. All right, so let me get some important points. Get those snipped in. All right, so this is the graph of that function. All right, so what we're looking for is where the profit is increasing. So it's increasing when it's going up and to the right.
Okay.
So the place where it's increasing is here, and we want the x values. So the x values, it starts at 0 and it goes to 3,400. And it's not any more complicated than that.
Okay. That's pretty easy. It's just
Yeah.
about doing the formula, the profit, and the
Get the profit, revenue minus cost, being able to graph it, which you can do, and then just getting the window. The window is a hard part because you'll initially see it down here and you'll be like, where is it? And I'll
yeah.
show you some ways to quickly get it into the right window.
Okay.
Okay, boy, the next one is the tough one.
Yeah.
All right, so the next one is it kind of looks like the first few problems that we were doing, but this time it's telling you that the graph is of the derivative and the rules change.
Okay.
So the things that you think were true with the original function are not true here. Uh, Find all locations of relative extrema and tell whether each extreme is relative to max or a min. Okay. So what I'm going to do here, which may not make much sense at the first glance, is I'm going to draw a number line, and we're going to bring down. Why? Huh. Oh, I'm sorry, I don't need that point. We're going to bring down these places where it crosses the x-axis. So this is at -9, -6, -3, and -1. Okay, that's thing one. So thing two is if it's above the x-axis, we're going to put a plus. If it's below the x-axis, we're going to put a minus.
Okay.
Okay. Now we do have to add one more little thing here. This is, I guess that's okay. We can, that's that. So now we can answer the questions. So, and this is like this would go on a note sheet, if you were allowed to have one. If it goes from plus to minus, it's a max. If it goes from minus to plus, it's a min.
Okay.
Plus to plus and minus to minus is nothing.
Okay.
So you're reading it left to right. So plus to minus here. So -9, it's a
Plus.
minimum. Max, sorry, max. Sorry.
Oh, yeah. Sorry.
I said the wrong thing. I'm just way off today. So it's going to be this right here. So it's going to be -9. And then from minus to plus is the min. And then from plus to minus is a max. And then again, from minus to plus is a min.
Okay. Trying to
So
find.
the rules are different for this one. You'll definitely want to look at this example. They tend to put this on the test.
Okay. So that one probably won't be. Okay. So for some reason, my question or my answers for this one are out of order.
If you closed and reopened the thing we're working on, sometimes the problems do change slightly. So just let me know if you see any differences.
Yeah, it's B instead of D, but it's still. And then I need parentheses, right?
No, this is just a
Nope.
list. It's a
Okay.
list. Yeah, it's
Oh, because yeah, so it's not. Okay.
all right. That's it for that. I mean, there's nothing more to do. The next one is slightly easier. Probably should have done the second one first, but it's okay. All right. So again, we're going to draw a number line. And we're going to identify the places where it crosses or touches.
Oh, okay.
So that's at -1, that's at -7. And if it's above the x-axis, it's a plus. If it's below the x-axis, it's a minus. I should have written that down somewhere. Above is a plus, below is a minus.
Okay.
It's the same rules. Um, the reason we're doing that again is because we're given the derivative. All right, so so when it goes from minus to plus, that's a min. Minus to plus is a min, so there's a min at -7. Wait, I might have put these in the wrong order. I did. So
Okay.
yeah, these need to be switched.
Okay. -6, 1 is first. Okay.
All right, so in our problem, there's a min because it goes from minus to plus, and then from plus to minus, a max is at -1, like that.
All right. Just my next one.
Is that okay?
Yes. Yeah. Sorry.
All right. All right, moving on here. All right. Find the x values of all possible points where the function has any relative extrema. So this problem is more like, sorry for all the scrolling, but it's more like this one here where they don't give you the graph and we graphed it. So you want to graph this. Definitely want to graph it.
Okay.
And squared minus 5x plus 2. All right. All right, getting the graph in. All right, so here's the graph of it. Yay, we got the graph. So this point down here in the bottom represents the min. And if you're thinking, well, hey, Matthew, why aren't we using these 2 points here? It's because we're given the original function. There's like two sets of problems. It's one where you're given the original function, one where you're given the graph of the derivative. They're different rules. So when it's the original function, you graph it, and you just literally look for like, where's the min or the max?
Okay.
All right, so the min is, it's a relative minimum of, so this is the y value, so minus 4.25 at x equals 2.5. And I guess double check that it's not asking for as a fraction or anything like that.
Okay. Because,
I did.
yeah, that should be good.
Is that okay? All right.
Yeah.
It does not have a max. These go up forever. So we don't, I mean, even though it would seem like, well, isn't that a maximum? No, it's actually not. It has to be infinities are not mins or maxes.
Okay.
All right, this is actually the same question as the previous one, just worded differently. It says use the derivative to find the vertex of the parabola. You don't need to do that. They're not going to check your work on it. You're just going to graph it like we've been doing, and you'll find the vertex. If you want, we can do it by hand, but would
No.
suggest yeah, doing it this way. So the vertex here is 2 comma 5. That is your answer, 2 comma 5.
Okay. Yeah, definitely easier to graph it. So.
Right. In the summer, the activity level of a certain type of lizard varies according to the time of day. All right, so here they're giving you the function. And I think it said something about it's like T hours afternoon. Could you just double check that after
Yes,
12 p.m.?
2
Okay.
hours after. Yeah.
All right, so we want to graph this again. And I'm going to go to Desmos and do that. I would encourage you to get that calculator and try some of these. But all right, so let me kind of give you a, when does it reach its lowest, highest? Does it say, maybe I didn't graph this right. Minus 0.288. Okay, does it say anything else like it's from noon to,
No, it just says the only part it cut out is where T is the number of hours after 12 noon. So it's
okay,
just
all right. Well, here we go. So the graph of this is this right here. So you can see that it reaches its peak at 5.084. So the thing that's probably uncomfortable is that like we're using decimals and this is in time. So if you take 0.084 and multiply it by 60, you should get 5 minutes. So this right here corresponds to 5:05.
okay.
And that gets you down to the two answers. Okay.
Okay.
And so now you got to decide, was it 5:55 a.m. or 6:55 a.m.? I believe this is more like what your midterm is like. you can see it's at 18.9. So what is that? Well, 12 p.m. plus 12 hours gets you to 12 a.m. 6 more hours gets you to 6 a.m. See how we're at 18?
Uh-huh.
So the 0.916 times 60 is going to get you to 55 minutes. So it looks like it'll be 6:55 a.m.
Okay.
Yeah, thoughts on that?
No, I think that's one of the ones they just have to practice it too with the graphing and
Yeah. All right. Where are we at here? Okay. All right, so this is the next one I see. For the function, find the second derivative, then evaluate the second derivative at 0, then evaluate the second derivative at 6. Okay. So we did a bunch of derivatives yesterday. Could you give me the first derivative of this? If you remember, you have to bring the exponent down and subtract 1 from
uh,
it.
4 times 4
Yep.
x 4 minus 1,
Good. 16x cubed. Keep going.
and then 3 times 3 x 3 minus 1, which is 9x squared.
Going.
And then 2x squared. Negative 4x to the first power, just x.
Good. And the derivative of just 3 is 0. Derivative of a constant is 0. Good. So you did so well with that. You're going to take yet another derivative.
Oh god, okay.
So keep going here. Same idea. Take that number, exponent multiply, subtract 1.
Okay, so 16 times 3. So 16 times 3, so 48 uh to x 3 minus 1 to the second power, 48x
Good.
squared. And then 9 then 18x.
When it's a number here at the end, a number times x, it just becomes the number.
Okay, so just minus
All right,
4.
so that's your first box. Very good. Job on that. The next two are evaluating the derivative at points. So at 0, it's 48 times 0 squared minus 18 times 0 minus 4, which you'll find is minus 4. That's the second box. And then the second derivative at 6 is 48 times 6 squared minus 18 times 6 minus 4. It will not be as simple. Definitely will need a calculator. I'm going to go over to the Desmos scientific calculator and calculate that. All right, so it's pretty large here. It's 1,616. Welcome to double check those.
I didn't do the first one. Okay.
Any questions, thoughts on that?
No, those ones I'm fairly confident in, I would say.
Yeah, good. All right, so new problem here. This one's awful. It's because you have to find the third and the fourth derivative of this thing. And if you recall from yesterday, this is a product rule. It's an F over G. Your F is 2x, your G is x minus 3, F prime and G prime. So the derivative of F is 2. the derivative of 1x minus 3 is 1. And then we learned yesterday the derivative is bottom times root of the top minus the top times root of the bottom over the bottom squared. Okay, so for our first derivative is x minus 3 times 2 minus 2x times 1 over x minus 3 squared.
Okay.
Now we do want to simplify, and the reason you simplify is because you're going to reuse the derivative. So this becomes 2x minus 6 minus 2x. On top it becomes just minus 6 over x minus 3 squared. And this, you might think, oh boy, it's another quotient rule.
Yeah.
Well, it could be, but that's not the best way to write it. You'd want to rewrite it like this, x minus 3 to the minus 2 power. And now when we take the derivative of this, because we need the third derivative, so we got to take 2 more derivatives, we're going to do this as a u minus 6 u to the minus 2, where u is x minus 3. We were doing this yesterday. So the derivative of this, the second derivative it's power rule. You're bringing this negative 2 down. So that's 12 u to the minus 3 times u prime. U prime, can you tell me the derivative over here of this?
So it'd be one,
One,
just one.
yeah. So this is 12 times x minus 3 to the minus 3 power times 1, which ends up just being 12 times x minus 3 to the minus 3 power. That's the second derivative. Almost there. Third derivative. Third derivative. So again, you could make this u over here, but the derivative of it is 1, so you actually don't have to. That's a small little wrinkle. So you can just bring the exponent down and subtract 1 from the exponent.
Okay. Okay.
So this is your first box.
Okay.
And then for whatever reason in calculus, when you go to the fourth derivative, you put the derivative number in parentheses. Don't make the rules, just play by them. That's what you have to do. Same thing there. You're going to take this exponent, multiply by the front number, subtract 1 from the exponent. And there's your next box like that.
Okay. I feel like on this one, like if there's one on the test, you're taking the derivative so many times, it's easy to like screw the whole thing up if you make one mistake.
Agreed. You can also, though, recognize the pattern. So from the original to the actual answer, you could actually sit there and like, I know you don't get a reference sheet, but you can almost be like, huh, is there a way to like, you know, figure it out? And there actually is like, but when you get to the exam, multiple choice, I'll try to give you some other ideas about how to do these problems. Like, I don't want you to get stuck guessing. That'd be terrible. So, next problem here. Which one, which problem are we up to, by the way?
We are on 12 right now.
Okay. All right, so find the open interval where the function is concave up or concave down. Find any inflection points. Okay. If you were to graph this, do you remember what the graph looks like without uh, seeing it?
No.
Okay.
Is
So this is
it
it's a
quadrilateral?
it's a quadratic, it's parabola. Do you remember if it opens up or down?
Um, I can't remember. I know it's based off the leading code.
Yes. So A is less than 0, so this opens down.
Okay.
Now you can still graph it. This just is like a, well, this is, it's useful if you know this, but not necessary. So it
Okay.
opens down. So concavity, concave down is looks like this. It either looks like this or like this.
Okay.
Concave up looks like this or looks like this. So sometimes students learn holds water for concave up, concave down does not.
Okay.
So I will ask you now, does this hold water?
No.
It does not. So this is actually concave down everywhere.
Okay.
Um, it does not have any what are called inflection points, but this is concave down everywhere. And it's never concave up. So that's from minus infinity to infinity.
Okay.
The next part, it says find an inflection point. An inflection point is where it switches from concave up to concave down. This does not have any. You might be wondering, well, what is an inflection point? What would one look like? The graph y equals x cubed is the simplest one that has one. It's got one right there. It switches from does not hold water to holding water. Sometimes students will like show their hand, with it like holding your hands up or palms up, palms down. Let me add that in here. Palms down, palms up, like that. Okay. The rest of this we can get to probably 30 minutes. Yeah, if you want to, if that's we do have some 30-minute options, or you could book a full hour and we could just move on to something else if you wanted. But
Okay.
that's going to do it for today.